Can you hear me okay? Yeah. Okay, so the third lecture. Today we're going to discuss another technique that goes slightly to lower masses for the dark matter candidates. That is the cryogenic crystals in general, but we are also, if we have time, also discuss some new idea with cryogenic superfluids also. The candidates that we will be looking into are, well, still the standard WIMP. Many of these techniques started for the standard WIMP searches, and then they evolved into looking for other candidates in lower mass ranges through the electron channel, because essentially everything has electrons in them. So some sensitivity, it's always there. So if you are able to lower your threshold, you will still be able to do these kind of searches, okay? So again, this is just a reminder. What are we looking for in a target? Now, we discussed this when we were looking into which noble gases or noble elements were good targets for dark matter searches. The same will happen here with solid state things like semiconductors or crystals or things that produce some kind of signal. Again, these things apply. We want to have nuclear recoil, electron recoil discrimination for the standard WIMP searches because the biggest rate is going to come from the interaction of WIMPs with nuclei because of the coherent enhancement of the cross-section. Then we want heavy targets, but again, heavy targets are harder to match kinematically with the dark matter candidates, so you will have smaller signals. At the same time, for this is also very, very critical that we have things that we can purify a lot and remove all the radioactive isotopes in them. So that will limit the amount of materials and elements that we can use for our detectors. Then, for the light dark matter, the problem is not so much having a large nuclei, but having something that you can have a very, very low threshold. So again, here you can go to elements that are semiconductors or semiconductor-like, and those will have a band gap that is relatively small. But the problem is that if you keep moving this thing to smaller and smaller energy differences you need to provide in order to excite one electron to see a signal, that will naturally have more dark count events that happen just because of thermal fluctuations. If you have something at a temperature that is different to 0, you will have thermal fluctuations, and some of the electrons will be seen as signal even though there is no external radiation coming into your detector, okay? So this is also one of the motivations why many of these crystals and solid state detectors go to cryogenic temperatures to remove all this energy excess that you have within your sensor that produces a signal even if you don't see anything from outside. And that is particularly important for phonons. I don't know how familiar you are with phonons. I'm not going to go into a lot of details with that, but here I'm going to discuss what's the simplest way of use something like this, a calorimeter, to look for dark matter or radiation in general, okay? In this case, you have an absorber that is made of a crystal, okay? We don't need to go into details into which crystal. It can be silicon crystal, germanium crystal, or things that are a lot more exotic. But you have a piece of material, okay, that it's cooled down, let's say, to a temperature that is very close to the absolute 0. So you have a thermometer here that is the link that is in between this absorber and a heat sink that is at millikelvin temperature. So in the long term, this is going to be everything thermalized at the same temperature that is going to be in the order of millikelvin, okay? And you have this thermometer here that you are recording the information over time, and you see that you always measure 0, okay? Then at some point, you have external radiation, okay, that can be a WIMP or something different, that produces deposits some amount of energy in this crystal. it could be through a nuclear recoil, or it could be through an electron recoil. What is important is that it transfers some of its kinetic energy to one of the elements inside the absorber, okay? And then what happens? When you have excess energy in one position, localized in space in one position, this will tend to just be homogeneous, uniformized, just thermalized, okay? How does this happen? There are several ways. One way is radiation, again, like scintillation, okay? So you have something that is excited, then that relaxes, and then it produces photons that go away. That is one possibility. What are other possibilities? I know we are all tired, but yeah. What are other possibilities? Okay, so the other possibilities are, for example, again, radiating other stuff, okay? You can radiate another electron. You can have an electron that moves through the material and produces secondary ionization because it hits other electrons, and then in this way the energy is split among other particles until it gets completely uniform. But the main way energy is lost in most materials is heat. Okay, what is heat? Heat is just movement in the element, in the nuclei. There are vibrations in the nuclei that you have in this material. Okay, and that is what I'm calling phonons, because you can describe these vibrations in the lattice as things that have similar properties to particles, although they are not particles, just vibrations in this net of atoms that you have there, but they can still be described pretty much as particles. Like if you have, I don't know, a string, you do like this, then that thing propagates similarly as a particle, okay? Okay, so you will produce heat here. This heat, because this is energy, this will just bounce around the absorber, okay? And at some point, it will go through your thermometer, and this link between your main detector and the heat sink, okay? And when that happens, this thermometer will rise its temperature because this thing here has a relatively small volume, so a small amount of energy, a small amount of heat can produce a large change in temperature in this thing, okay? And then this thing will go up in temperature, and the difference in temperature will be given by the amount of energy that you put inside this small thermometer divided by the heat or thermal capacitance of this thing, okay? Very similar to what you have with a capacitor that you put, some charge and it changes the voltage, okay? So this goes up, but over time, the phonons keep bouncing around here, and they flow through this link to the thermal bath, and you will have a signal that looks something like this, okay? So this is very nice because, everything produces heat. It's the thermal death of everything, okay? At the end, we are all going to be heat, okay? So you will have here a signal that is kind of guaranteed if you transfer some energy into your target material, but then you need to be able to record this, okay? And this is not going to be simple because we are looking at millikelvin temperatures, things that need to be read pretty fast. And then there comes the question of how do we build a thermometer that has microkelvin resolution, okay? And also a time resolution in the order of milliseconds. That is not easy. If you tried measuring your temperature when you had COVID at some point, you know that it takes a long time and the reading is really bad. Okay, so how do you do that? Well, you look for things that change their behavior a lot when you change the temperature, okay? And when these things happen, one situation where these things happen is when you are close to a phase transition, okay? For example, when you are going from water to solid in ice, okay? you have there that a change in very few degrees changed dramatically the properties of the material that you are looking at. And in this case, what we are going to use is the transition between superconducting and non-superconducting states in a metal, okay, or any material. So in this transition, you go from a resistivity that is close to zero, okay, or zero, and to something that is not zero. In this case, around 100 milliohms. That I know milliohms looks small, but it's well within the reach of technology to measure that. So you will have here that a change in a few millikelvins, okay, will produce this huge jump in resistivity. And in this range, it behaves close to linear, okay? And even if it's not linear, you can calibrate this. But let's assume that it behaves close to linear, okay? And you operate your detector at, at this temperature, okay? So you select the thermal bath here. So this thing is at the operating temperature in which your thermometer changes the phase, okay? And that's the only temperature that you can operate this thing at, okay? And you have to be very precise. But you do that, you get there a resistivity, let's say, of 50 milliohms, and then that's your operating point. Whatever deviation you have from that is the temperature changes that go through your thermometer, okay? And you can measure a resistivity pretty fast, okay? So this has the two properties that we wanted from our detector. This is just one of the options that are being used for thermometers, but it's the one that we are going to stick because I don't have a lot of time to discuss other, but we can talk about those other options during the coffee break. But this is the one that it's most widely used. Okay, so just summarize, you have energy in the absorber that it's in the order of keV or so. Then you have a temperature rise in this transition edge sensor. That is the name of this technology. That can be in the order of microkelvins, and the resistivity changes in the order of milliohms. Okay, so now we know how to do this. And for you to get an idea, this is nothing super fancy, okay? The transitions air sensors are also very nice because they are super simple. This is a picture of CREST 3. This is the experiment that I will be using as a benchmark to explain or tell you about a little bit more about these technologies. Then I'm going to move to another experiment that is called Super CDMS to talk about other slightly different detectors. There are lots of experiments and variations on this technology. I'm just going to stick to one to talk about the detection principles. Yes?
Thank you. So I have a question about the previous slide.
Yes.
About the resistor. So basically we have this resistor that changes linearly within a range. So it means that we know beforehand, before doing the experiment, more or less what is the range of
Yes.
temperatures.
Yes.
And how do we know before using, I mean, in this case, we would need another thermometer to estimate, right?
Yes. So, I mean, all these things have been extensively calibrated. And the thing is that you don't need to calibrate each individual TES, because the thing is that the resistivity and the transition only depends on the properties of the material. So let's say in this case, you are using a tungsten thingy, okay, to measure what's the resistivity of this thing. So that is something that never changes at all. And you can measure the resistivity and the properties of these things with systems that are much higher and in which, I mean, a lot more convoluted. But once someone has measured this, then you are good. But how do they calibrate and do the original measurements to say tungsten has these particular properties? I don't know. I need to look into that. But that's done by material scientists, and I don't know what's the technique used there. But this has been measured with extremely high precision.
Oh, okay.
Okay.
Thank you.
But yeah, so in this case, for crest, so this is the white thing here is the absorber that we had in yellow here. Okay, so this is the crystal where you be looking at the interactions with radiation. And this thing here is the transition edge sensor. That here is a close-up. So what you have is this dark gray area and this other dark gray area that are just metal aluminum foils that are deposited on the crystal that you use for two things. One thing is just to connect this to a bias on one side and the other one to a bias on the other side. So you have a current flowing through this, and then you can measure what is the resistivity of this thing. This thing is just a resistor in a way, okay? And these things are large also to be able to collect the phonons more efficiently. So remember that I told you that you will have these vibrations, phonons, bouncing around the crystal until they find a way out. And the way they find their way out is by hitting one of these aluminum foils. When they hit that, then that transfers the heat into this small part that is the transition edge sensor itself. Okay? They are just collecting heat and moving it into this thing. And then the way out for cooling out this huge crystal is just a hair-like cable that is connected to the tungsten rectangle there. So all the cooling is done through that, which is crazy, okay? So these are called wire bonds and are cables that are the size of a hair or smaller, okay? So you have your crystal here, things going out. This hair here is the thermal link, that is this thing here, okay? So this is very nice. Oh, just for completely, this thing here is a heater that they connect to an outside source in order to introduce pulses of heat and see that everything is working. But it's not a detector. It's just there to cross-check that everything is connected and looking good. Okay, so you see that the design of this, it's very, very, very simple, okay? So how can we improve on this? I told you before that heat is one of the ways that you can distribute the energy to get to an homogeneous state, but there are others. As I said before, we have possibility of producing photons there. So we will always have phonons, okay, in an interaction, but I don't know if you can see that, but these ones, here it says photons, okay? So you will also produce light. And many of the materials that are selected for this are so that they also have properties of a scintillator, okay? So you can excite the electrons there, and then when they de-excite, they emit light, and you can place another sensor close to this one to be able to see those photons. And the reason behind this, you probably already guessed, is that it's twofold. On one hand, having more ways to collect the energy helps you to actually see a signal, okay? Because if you are losing all the photons, that they just go away, then the signal is going to be a fraction of the total energy, just the phonons. If you collect both, then you have more chances of seeing something and going to lower thresholds. The other thing is that, again, you want to have electron recoil, nuclear recoil discrimination. And remember that in noble liquids, what we have is that the amount of light that is produced compared to the amount of ionization that is produced depends on if it is a nuclear recoil or an electron recoil. Well, The same happens here. The amount of the photons that are produced compared to the amount of phonons that are produced depends if it is a nuclear recoil or an electron recoil. And what is very neat about this idea also is that this detector, that is a light detector, okay, essentially uses the same technology as the main detector that you have there. So what you do is you place a different material that has the capability of stopping these photons that are coming out from your main absorber, okay? And this is typically a different material because you want your absorber to be transparent to the scintillation photons that are produced, but if this thing was made of the same material, then it would be transparent too. So you would not be able to see those. So you select a different material for this thing that is not transparent to the photons, and then you look at the heat that is deposited by these photons into this second detector or absorber, okay? So here is an example of the two signals by a crest detector. So you have the phonon signal, that is the one in red, and then in coincidence, the light signal. Because look at the time scale of this. This is milliseconds, so these are relatively slow detectors. And the light, because we are talking, I mean, takes essentially no time from here to here, because these are detectors that are this big, okay? So this idea has been implemented, and here is another version of the crest detector. The crystal is here on the back, okay? And this rectangular thing here, you can guess, is the light detector. There you have a transition edge sensor coupled to the thermometer, okay? And again, you can see that all this is enclosed in copper. The reason for that, you already know, is that copper is one of the things that we know how to purify best. So a lot of things are made of copper because there are no radioactive isotopes of copper, and you can do a chemical separation of copper of everything that is radioactive, or most. So the crystal that they are using, you can see here, is calcium, tungsten, oxygen. So this is an exotic crystal. It's not a single element. In this sense, it's similar to the gamma crystals, okay, that you have many different targets there with different number of nucleons in them. So you are able to use this thing as a multi-target target, okay? Because you are able in this way to have things that are heavier to see heavier masses for dark matter candidates, and you have nuclei that are lighter to be able to see or have sensitivity to light dark matter candidates where your flux is higher and you don't need as much, okay? Enhancements in the cross section. And the size of this thing is a few centimeter cube, okay? So we are talking about really small thingies here. And here, what I'm showing, this is the theoretical expectation, okay, for the electron recoil, nuclear recoil discrimination. In the x-axis, we have the energy that is deposited or goes into the absorber. And in the y-axis, this is light yield. Is just a fraction between the total energy and the amount of energy that goes into light, okay? And what you can see is that, well, you have different regions here, and some of these is because some of these regions correspond to tungsten, some of these regions correspond to oxygen recoils, okay? So these two lines here are nuclear recoils from tungsten and oxygen, okay? And then the brown region on the top is the electron recoils, that those don't depend of which, I mean, where the electron came from, if it came from an oxygen or a tungsten, okay? So you can see that these two are very separate, very easily discriminated at relatively high energies, but when you go to low energies, everything becomes mushy. And that is reasonable, okay? Remember also this happened with the novel liquid detectors, when you go into low energies, you only had essentially one signal to look at, and then the estimator for the ratio of these two things doesn't make sense. The fluctuations are huge, so you don't have any discriminating power at very low energies. And unfortunately, that's where you want to look at, okay? But still, this provides a very powerful tool to identify your backgrounds and also to understand how your detector is working, and also at some energy range to provide discrimination, okay? This green band here is alphas, okay, that behave something like in between the two. So if you have a radioactive element that decays and produces an alpha, it's not exactly the same as this heavier nuclei, but it behaves more like a nuclear, but much lighter, so closer to an electron recoil, okay? So that was calculation. This is data, calibration data that they took, and you can see that it works pretty well. I mean, it's not perfect, but it really has a big discrimination power at higher energies. But when you are going to lower energies, as expected, everything becomes less clear. Still, you do have some discrimination power, but it's the spill from the electron recoil into the nuclear recoil is big. Okay, so it's much harder to get a clean sample. So this was a calibration run. This is not what they use for looking for dark matter. Okay, so to look for dark matter, you place the same detector that you have already calibrated and completely characterized inside the shield, and run some time with this and collect data. Okay, and that's this plot. Okay, so now you can see how real data for these sensors look like, and at high energies, okay, no nuclear recoil candidates at all. Okay, nothing. So super clean. But you also see that there are a lot of electron recoil events. And this is just to illustrate something that we've been discussing a lot, that the main background contribution is coming from electron recoils, okay, everywhere. So you can live with a much noisier environment if you have electron recoil, nuclear recoil discrimination. If you don't have electron and nuclear recoil discrimination, you can still have an experiment, and there are plenty of experiments that run like that. You just need to be aware that the impact of any radiation in the environment is going to be much larger, okay? So, but what happens when we go to lower energies? So when we go to lower energies, well, what we see here is essentially a lot of events, okay? And even before that, in this region, we already start seeing candidates for nuclear recoil events. Can we guarantee that these are nuclear recoil events? No, we cannot guarantee that. They can just be spillover from the electron recoil channel, okay? But we don't know. So, oh, sorry. Here, okay, I don't know if you can see that, but there is a kind of a lighter shade of black, okay? Here, this is the region that they use to look for dark matter. So again, they are playing the same kind of trick that we discussed before, that you can pay half or more of your efficiency in order to get a cleaner sample. So what they do is exactly that. So they say, okay, I'm willing to only consider the nuclear recoil events that appear in this shaded area, reducing my efficiency by about 50%, but I'm going to reject all this trash that is here, okay? So I'm going to have a much cleaner sample to look for WIMPs. And when they do that, they place this limit. This is a limit that was produced in 2019, so a few years ago. And since then, they have kind of hit a wall. And I'm going to go into details on what happened there, or what happens there. There are some new results from CREST. That is a beautiful experiment. But most of their focus has not been in really improving the sensitivity so far of the experiment, but understanding where these low energy events are coming from, okay? Because that is what is really limiting their reach, their science reach, okay? So here, I'm just projecting all those, I'm just projecting all these events into the x-axis here, okay? And that's what you see. So in gray, we have everything, all the events, all the dots that we had in the previous 2D plots. And in red, we only have the events that are in this shaded region, okay, the selection region. So you see that here we have a huge spike, okay? And if we look closer into that, it looks like an exponential-ish decay. And unfortunately, that is exactly a signal that you would expect from a WIMP, okay? So if you have a background that mimics exactly the kind of signal that you expect for the thing that you are looking for, that really, really kills your sensitivity, because you cannot really move forward if you know that this is a background, and for other reasons than they are not claiming that this is a discovery of dark matter. But then it really limits your science reach. And they know that this is no dark matter because of many reasons. Because of many reasons, but I'm going to discuss that later on, okay? So they've been focusing on understanding where these things come from. And they tried, over these 5 years, a lot of stuff, okay? So here, this is a slide from the CREST presentation at IDM last week, okay? And they are just showing all the things, or some of the things that they tried. So they said, okay, maybe this is related to the target material. It's not as clean as we believe, or it has some problems. So they changed. Instead of using the elements in the crystals that I showed you before, they used different elements. They grew crystals in their labs, do stuff. They still have this excess, okay? Then they try different techniques for growing the crystal, which can be very, very important, because any defects on the crystal can create intermediate energy levels that then have a different behavior. This also didn't produce any difference. Then they remove the scintillating materials from the crystals. You can do that, for example, by using silicon. Silicon does not scintillate, just pure silicon. So still the same problem with the excess. Then they started looking at stranger things, like, okay, well, it is true that we have a detector that it's not really coupled to the external world by anything, but that is not real. I mean, that's not reality, because you have in some way to mechanically hold this thing in place. So there are these clamps or holders, okay, that can introduce mechanical stress, or can produce events. Let's say that you have an event here on the clamp, and then that goes into your sensor, but only deposit a fraction of the energy, not the full energy of the event. So that can also produce this low energy excess. So they tried changing these things by different designs that didn't change. They even went so far as to make these holders of the same material crystal that they have inside, and put a transition edge sensor on each of these holders to see if there was any flow of thingy. So the complexity of this started scaling up a lot, but unfortunately they did not really were able to pinpoint what was the problem with this. And none of this really produced any measurable improvement. The idea right now, and I will go back into this later on, is essentially that maybe this is linked to some kind of mechanical stress and relaxation within the crystal itself, okay? it has been known from the beginning of this technology that if you introduce some mechanical stress, you will have fractures and microfractures and things that produce an excess of low energy events. That has been done, but they did a lot to reduce this stress. But still, what they do see, this, and this is one of the reasons why they know that this is not a dark matter signal, is that in the y-axis is the number of events per day, okay? And in the horizontal axis is just time, days. So these are different runs that they did with the detectors, okay? And you can see that when they, in these shaded regions, here, for example, they were operating at a millikelvin temperature, at the temperature that they need to operate, 15 millikelvin, okay? And then, for some reason, they raise the temperature to 60 Kelvin to do some work or whatever. And after that, they had a huge spike on these single electron events. And this is already at the operating temperature. If not, you cannot read the transition edge sensor. So this is already at 15 millikelvin. But then you have a very long relaxation time that takes many days, and it's not clear why that is happening. If you make a change in temperature that is smaller, you still, well, it's not super clear here, but changes in temperature that are smaller don't produce as a big effect, but they still produce an effect. For example, here with 30 Kelvin, you see a spike, but not as big as 60 Kelvin. And when you warm up to 130 Kelvin and then start reading up, you again have this huge spike. And this is not the behavior that you would expect from dark matter, so they know that this is no dark matter. But it's also not clear why this is happening, okay? And one of the ideas is that, yeah, there are some internal stresses in the crystal that when you warm up and cool down, well, you know that things change the amount of stress and how these things are distributed. So when you cool down, you may still have some remnant stress that is slowly being readjusted. But it's not clear. But we will discuss this further on in the talk. So now, that was the end for CREST light detectors. Now I'm going to discuss a slightly different technology, but that is very, very similar to the one that is being used by CREST. Okay. The idea here is very similar. Is again, we have an absorber, okay, and as always, we will produce phonons when there is an energy deposit, but instead of selecting a material that produces scintillating photons easily, here we want to select a material that produces ionization easily, okay? So you have ionization here, and if you just leave it like that, those electron holes or ionized nuclei and electrons will just recombine in place, okay, producing more heat or photons. But if you apply an electric field there, similar to what we did with the novel liquid detectors, the TPCs, then you will not allow time for these things to recombine. You will separate them before they can get together and become neutral again. And then what you will have is that these things start splitting and going to the two different sides of your sensor. So if we now have here our thermometer, then we will measure this spike in temperature. This is the phonons signal. Then, because the electrons drift very slowly, the same as they did in novel liquids, you will not measure any current flowing through this thing yet, or you will measure the steady current that you had before. But at some point, well, all the phonons go away. These things go into your cables that you have there. You have here a current sensor or some way of measuring the charge flowing through that, and you will have a second spike that is related to the amount of ionization. And again, here we will be playing the same trick that before. We are looking to use the ratio between these two signals to have electron recoil, nuclear recoil discrimination, and also to be able to to collect more of the total energy that has been deposited there. This is an ICP detector that is one of the super CDMS sensors that has essentially this design. We are looking at this from the top. This is about this thick, so it's about this size and about this thick. So it's like a pack, I don't know. And all these lines that you see on top we are going to look at those in details, but are ways of collecting phonons and ways of collecting charge, okay? And again, this thing is inside the copper box as usual, okay? So now if we look at those lines from the top in detail, they have a structure that is like this. Each of these blobs has this structure in them. So these are aluminum fins or gold fins, and then these things here are the transition edge sensors made of tungsten or other materials, okay? So these things are collecting the phonons that are produced in the crystal and giving you a signal outside. The same, well, I don't know if you can see that, but in between these lines that are just a string of transition edge sensors, you have another line that is just there as a contact to collect charge, okay? That is producing your sensor. Okay. So, oops. So this provides electron recoil, nuclear recoil discrimination. Another way of operating these sensors is what it's called the high voltage mode, which it is a very interesting way of using these sensors and provides the best sensitivity to low energies, okay? And the way this works is the following. Remember that before we had this voltage that was in the order of a few volts, so this was a relatively small voltage, and the drift of the electrons that you produced and electron holes that you produced in the crystal was small, and you did not provide enough energy to really accelerate these things a lot. But if you keep increasing that voltage to a high number, then what you will have is something that is similar to what happens in a PMT or similar to what happens in the extraction layer in the gas pocket in TPCs, that you provide enough energy to the electrons there so they accelerate and they hit other electrons or nuclei and they produce secondary signals. Okay, so this produces amplification. And in this case, what you are using is these crashes between electrons and holes and the lattice itself to produce phonons, that those are the easiest to produce. In order to ionize further, you need to provide enough energy to the electron so it can accelerate and hit another electron to be ionized. But that's a lot of energy. So that is in the order of EV that you need to provide. This, in order to produce a secondary phonon by just crashing with nuclei or the lattice itself, you only need to provide milli-eV. So you will produce a huge amount of phonons compared to secondary ionization. So the trick here is something slightly counterintuitive, is that you accelerate these things by applying a high voltage. When you do that, when you apply a high voltage, your sensitivity to actually seeing the original charge gets completely ruined, so you are not able to see the ionized charge directly using your current sensor, okay? But you will produce a lot of secondary phonons. But those phonons that you produce are linked to the amount of ionization that you produce at the beginning, not to the amount of phonons that you produce at the beginning, okay? So what they are doing here is using this technique to measure ionization only, okay? Because also with this huge amount of secondary phonons that are called Luke-Naganov phonons, what they do is also they completely bury the original signal, the original heat signal coming from the primary interaction, okay? So this big signal that is coming from the secondary phonons is produced by the ionization that was produced in the original interaction, not but by the phonons that were produced in the original interaction. Is that clear? I know. Okay. So in a way, this, although they are measuring phonons, this is just an ionization detector. Okay. They are not really having this electron recoil, nuclear recoil discrimination anymore, because you only have one signal, and the only signal that you have is ionization, even though you are measuring the ionization through a phonon channel using this amplification. Okay. So the super CDMS program it's very large. It's one of the largest experiments in the US for looking for dark matters, and they are targeting the WIMP masses around 1 GeV. The reason for this is that for higher masses, well, you completely are dominated by bigger detectors, like the xenon detectors that we discussed yesterday. And for lower masses, this, as we will see, is not necessarily the best technology. But there is a range around 1 GeV masses in which this is the best way to go. Okay, so these sensors, they are going to have a lot of them, okay? And they mixed between germanium sensors and silicon sensors. In this case, because you are looking at charge, at ionization, at the same time as phonons, you have a smaller selection of materials that you can try compared to CREST. Because here you need the materials to be semiconductors, and there is a limited range of options there. Germanium and silicon are the best understood and the ones that industry has the knowledge to produce. Okay. There are other possibilities, but these are by far the two easiest ones, the main ones. So they are putting many of these detectors and interleaving some of the ones that I told you before, the ICPs, that are the ones that are measuring at the same time ionization and charge to be able to have, ionization and phonons to be able to have electron recoil, nuclear recoil discrimination, together with other detectors operated in the high voltage mode. They do this in order to have a wider range of sensitivity to all the masses that go from lower masses to higher masses. Okay, and they place these things in copper towers that look like this. They stack a lot of these things in one tower, and they have many of these towers all together that need to be operated at around 50 millikelvin, which is very low, so you need a huge infrastructure in order to be able to cool down all this mass, that is about 30 kilograms in total, of target material. If you include there all the copper shielding, casing, and stuff, it's a lot of mass, a lot of material that you need to cool down to millikelvin temperature and extremely stable. So all that is placed inside a copper cryostat, okay? That is then placed into a neutron shield, and then that is placed into a second lead shield, and outside another shield that is made of polyethylene, also to shield from environmental neutrons. Okay, and you have some openings there that are for the dilution refrigerator that is used to cool down to millikelvin, to the electronics that is on the other side. So this is a very big program, and this will start commissioning likely maybe the end of this year, maybe next year. We will see when we have the first data. Before the full system is commissioned, they will have data from a demonstrator that is also running at SNOWLab. I didn't mention this, but all this is installed in SNOWLab, that is an underground laboratory in Canada. Okay, similar to what we had in Gran Sasso, but the difference here is that it's not a tunnel that it goes through a mountain, but an active mining operation. So you go underground, so you cannot drive your car into the lab. It's a lot harder to get there, And it's a very harsh environment. We will talk a little bit more about SnowLab, but it's absolutely an amazing facility where to run. And the shielding provided by the ground at SnowLab, it's bigger than what you have in Grand SAS, so even smaller flux from cosmics. These detectors do have timing capability similar to what we had with the liquid noble gases detectors, noble element detectors, so they can use active veto, and they do, okay, which is something that is very nice to have. So these here are the projections. I'm not going to go a lot in depth with this, but again, so look at the mass range for the candidates that they are targeting, and it's something slightly below 1 GeV to about 10 GeV. Here you have the other experiments with novel elements that take over, but in this range that is very close to where the shoulder of the neutrino fog is, okay? This is the region that they are targeting on. This is the beryllium solar neutrino flux, okay? So you can see different lines here. The different lines are coming from the different operation modes of the detectors. The high voltage go to lower masses, okay? Both silicon and germanium. Silicon goes slightly lower because it's a lighter nuclei, so it's, but this is, yeah, I'm going to stop there. We can, and then you have these ICP that are the ones that have nuclear recoil, electron recoil discrimination capability for germanium and silicon, okay? So this is the prospect for their sensitivity. And now let's go back to this excess, because what happens is that in the demonstrators, all the super CDMS sensors and I mean all the detectors that are cryogenic crystals do have this excess in low energy events. All of them, even if they are looking at light, ionization, or other stuff. And nobody claims that this is dark matter because the rates are vary widely, and they are not consistent. They have a time dependence that depends on things that you do outside. So this is not a dark matter signal. This is a problem or an issue with all the detectors. But it's very strange that many different technologies have the same effect. They see essentially the same thing, even if they are looking at different stuff and using different materials. So this here, again, just to give you an idea of how big this problem is within the community, is a slide from the IDM conference last week, okay, in which they dedicated a full plenary session to discussing this excess, okay? And this is just one slide summarizing essentially there are no clear ideas of what's going on there, but everybody is kind of getting together and trying to solve this problem, or at least understand it. So some of the things that we discussed are included in this slide. The favorite explanation seems to be this, but nobody really knows, okay? And here I'm going to discuss some of the hints that are around. So these things here are, so this was taken from this paper that was also presented in IDM. This here is a small crystal with lots of TES on the top, okay? So this is one of the standard absorbers that we discussed so far. And well, they have to hold this thing somehow, okay? So what they did originally was to just have some glue to hold it into a copper mount there, a copper base, yeah? So, and what they see is that when they do that, and then they observe this, they observe some microfractures that are coming from mechanical stress. Very small, but still, we are looking at things that are milli eV here. So very small effects can have a huge impact there. And then what they did was, instead of gluing this sensor to the copper base, they just place it there, no gluing, okay, and did the wire bonding, okay, so connecting these things to the readout electronics with these hair-like cables, and that was it. So it was hanging from the wire bonds. You can only do this with very small things, but it can give you a way of understanding what happens with something that is just suspended in hanging from these hairs, okay? And what they saw was this. So this, again, in the horizontal axis is energy and number of events, and the red histogram here is from the detector that was glued. And the blue histogram here is from the detector that was just hanging by these hairs, okay? And they do observe a big reduction. It doesn't go to 0, okay? So the problem is not solved, but there is a big reduction. How important or meaningful this signal is, it's not clear. So on one hand, we already knew that mechanical stress can produce these low energy events. And yeah, for sure, you are going to have more mechanical stress here because there is also a thermal expansion coefficients mismatch between silicon and copper. Both things expand and contract at very different rates when you change the temperature. So you would expect that there would be a pretty large stress here compared to something that is not glued. So how important this is, it's not clear, but it definitely gives you a hint, or at least something to dig into and try to understand if you can reduce this stress by changing the way you treat these crystals. And that's the end. I don't know, there are 3 minutes. Do I have time to discuss something, or if there are questions, we stop here? Whatever. And maybe one of the questions will trigger what I want to talk about next.
Excuse me, you said that the basically the detector was hanging by cables, right?
Yes.
And what if you use, I don't know, electromagnetic or disinterfering something?
Levitate these things?
Yeah, yeah.
I don't know. As far as I know, that has not been tried. Most of these things are non-magnetic materials. So you would need still to add something that you can somehow control. But yeah, I mean, I don't know if that has been, I don't know that has been ever tried, but maybe, yeah. At some point, if people get desperate enough, they will do it.
Okay, thank you.
Can you go back to the plot with the low energy excess in the crust experiment? The one that you said the signal would look like a WIMP?
Yes.
Yeah. I have 2 questions. First, what would we expect for just standard model particles in this plot?
From just what?
Like, what would we expect for only standard model particles in this plot? And the other one, if they did studies with different WIMP masses or just half GV?
Oh, no, yeah. So they do studies for all the masses that you want to target, okay? So there are simulations and predictions. You have actually, in order to produce a limit or do a search, you really need to have an expectation for your signal. So there are, and you can compute what is the expected signal for WIMPs for all the different masses and size, and strength of the cross section. Okay, so that's done. I'm just showing one because this is the one that best fits this particular histogram. But yes, there are. So that's regarding the signal. And what you expect from only standard model particles, it's harder to answer because the thing is, you can definitely have this result just from standard model particles if the background, if the radiation environment is selected so it does so. So it's not something unique from from WIMPs and standard model particles. What you do is you build your shields, and ideally it's to build your shields so the backgrounds have a shape that is as different as possible from the signals that you have. And that's what we are doing when we are placing these things inside neutron betons and lead castles and things like that to reduce the amount of environmental radiation and just allow a fraction of that radiation to go in, and then we compute what's the shape of those backgrounds using Geant4 simulations or other means. And in principle, what they expect here essentially would be a flat background, okay? And that's not what they see. But in a way, we know that this is caused by standard model particles. So you definitely can have a way of producing these types of signals with standard models. I mean, one of the things that is really unfortunate regarding WIMPs is that the signal that you expect, essentially for the low masses, pretty much is just an exponential decay. And it's very, very simple to get an exponential decay from regular stuff, okay? So if you are looking at other candidates at higher, that are not WIMPs, for example, if you are looking at dark photons, some of those actually predict a signal that is just a line at a particular energy. That is the mass of the dark photon. So that is very different from most of the environmental backgrounds that you are able to reach. But unfortunately, exponential decays are very common.
Okay, thank you.
Any other question? If not, I have one. What are the possible solutions?
Okay. So, there are many. People are trying a lot of stuff, but one that may be very nice, that it's a radical new direction, is this one. Is instead of using a crystal as an absorber, what you do is you use a superfluid medium, in this case helium. And the reason for using a superfluid liquid here, in particular helium, is twofold. Well, once you have a liquid, you cannot have stress. So there is no mechanical stress there. Then the other thing is that when a liquid is in a superfluid state, essentially what it means is that all the heat is shared equally among all the particles there, all the atoms there. And that translates into an extremely low rate of evaporation. So if you have any regular liquid not in a quantum entangled state, okay, even at very, very low temperatures, you will have some evaporation because the distribution of energy between the particles just follows ideally a Boltzmann distribution, and some of them will have enough energy because they will be in the tail to just fly away from your liquid. But in a superfluid medium, that doesn't happen. So all the things are bound together. You don't have any evaporation at all, guaranteed. Okay? So then, if anything evaporates from this, is because something from outside just kicked it. Okay? So that's what they are aiming for in this design. You have a superfluid liquid, then you have an interaction, and when that happens, you deposit some energy. Again, this energy will produce phonons now that they bounce in this volume, and at some point they are absorbed by one of these helium atoms, and that atom evaporates, just a single atom, okay, evaporates, and you hope to see it. Okay, so you place here one of these detectors that detect heat, okay? And this atom, when it evaporates, it will hit your detector here and then produce a measurable temperature change locally that you can measure. That's a big challenge. It has not been demonstrated yet, but a lot of people are working on this idea. And from the detector point of view, it is very nice, okay? But there are many, many challenges, of course, related to this. But maybe at the end, the solution, it's not coming from the crystals, maybe it's coming from liquids.
We thank Javier. And now we move to the question to the three speakers. So, who wants to start? Okay.
For Dario, how can you have phonons in a liquid medium?
So, I mean, it's the same. So, similar to what, I mean, the analogy with a string that you do like that, the string is fluid, okay? In a medium, you have, just vibrations from one atom that translates to another, and you can have modes. Everything is linked. It's not, the description is not the same as a crystal in which you have things that are very tightly bound, but it's similar. So it's an ordered medium, more like random position of atoms, but still you can have wave-like propagation of stuff there.
Okay.
Okay. Any other question? Where?
I have a super basic question. So what's the difference between the beam dump and fixed target?
Well, usually you say fixed target because something is aligned. So beam dump is the target experiment, but it's a fixed target experiment. So usually you think of the beam between beam target and fixed target, and you stay fixed. Sorry, I forgot. Okay, so I think you can usually, I mean, there is no strict rule, but you can draw a line between a situation where you have your target, your beam impinging on your target, and the average number of interaction is lower than 1 inside the target, or is much larger than 1. So, for example, HPS, it has electron beam impinging on a thin target, and what happens many times is that the particle beam crosses the target without interacting, and that is a thin target. Otherwise, if you think of a beam dump, it's a fixed target, and it always happens something. So it's really rare that an electron goes through, of 100 GeV goes through a few meters of aluminum. So I think that you can draw the line in that sense. Then you have also, obviously, mixed situation, because you can have multiple interaction in a thin target, or I mean, target that does not contain completely the beam, but still you have some shower initiation. So it is a bit of gray area, but usually we define the difference like that. So that's it.
Thanks.
Thank you. Questions?
I have just a question about this presentation. There was, during the scheme of one of the experiments, there was bias I plus and bias I minus.
Yes. This one?
Yes. I just was wondering, what is exactly bias I plus and I minus?
Oh, it's just that this one is connected to a voltage, and this one is connected to another voltage, so a current flows through the tungsten link between them, okay, just as a resistor. And outside you measure the amount of current that is flowing, or the voltage drop in this resistor, just to estimate the resistivity, okay?
Okay, thank you.
So I have a question about the last slide you showed, because the way you talked about these new detectors, new generation of detectors, I didn't feel very confident about we seeing one unity of helium atom and detected So how, you said it was very challenging to really detect, but how are we going to do this? It doesn't feel like we will have a great sensitivity with this kind of experiment. I don't know.
I mean, yes, I share your concerns, yes. The thing is that, I mean, we do have technologies in which we are able to see single quanta of stuff. For example, looking and seeing single photons, it's something that we do regularly. Looking at single electrons in even EV scale electrons is something that we also do regularly. This is something that has not been demonstrated yet, but it's not impossible in principle. I mean, it will depend on the amount of kinetic energy that this atom has when it leaves. So if you have something that it's living with, I don't know, MeV kinetic energy, then yes, it's super easy to see one single atom that has MeV energy, okay? But if we are aiming for something that is in the scale of EV kinetic energy in a full atom, then that will be a lot harder. But still, I mean, it's not impossible. The first, I mean, my impression is that the first iteration of these things, if they work, well, they will have a relatively high energy threshold. Okay, they will only be able to see atoms that come out from the liquid with a high kinetic energy. But at some point, well, if the idea doesn't, I mean, it may have other problems. So the thing is, at this point, it's just a concept. And there are demonstrations of some of the elements here. But it may be that when you put everything together, everything looks good, even if your energy threshold is high, and then you start putting a lot of effort in lowering the energy threshold. Or it may be that when you put everything together, you see something similar to this low energy excess or other problems with other experiences. Okay, now this is not the way. But at this point, we don't know. Yeah.
Good. More questions? Okay.
I have a question for the three lecturers, just out of curiosity. My impression so far from the lectures is that we have been mapping for WIMPs on many situations, and so far everything has not worked out. Do you think that when we finish this quest, will we find any evidence of WIMPs, or should we start shifting our search to other candidates? It's for the three of you. What do you think?
Okay, I can start, but
I can go first. I think that we already started shifting to other things, not necessarily shifting in the sense that we are stopping studying WIMPs, but we are just trying to see if there are other reasonable possibilities. At the same time, it's worth going on with WIMPs. So I think that at the end of the day, it's right to go in different direction and to try to search for all the many possibilities that we have. If we have some reason to believe that one candidate or one theory is more motivated than other, it's reasonable that larger efforts are going to that direction. But still, I think in general, already there are several candidates from a really very low mass to WIMPs and over. So it's already happening, I think. I don't know what else.
I mean, yeah, definitely. We have to just find new places to look. So from the neutrino side of things, one thing that we can look for is cosmic ray boosted dark matter. So if you look at light WIMP particles, the problem with detecting them in your experiment is they just don't have enough momentum to give these nuclei or electrons enough of a kick to be able to see over your threshold. So one potential solution to that is assume that there is some ray, flux of cosmic rays coming from the galaxy center, which we know does exist, and say that those cosmic rays can give your WIMP flux between the galaxy center and your detector, a little bit of momentum in the direction of your detector, enough to make those WIMPs have enough kinetic energy to make some signal over your threshold. And so that's a signal that we search for in neutrino experiments that can give you, hundreds of MeV of, say, electrons that would give you directional information, be able to point back to the galaxy center. And that would be another way to, with some model dependence, say that you could discover that sort of phenomenological dark matter candidate. So yeah, it's again just finding new ways, new places to look if we continue to not see the stereotypical WIMP.
Yeah, I mean, I fully agree with what was said. So the community is already been shifting for some time already. My personal view for the WIMPs is that at some point it was the best candidate for many motivations. Most of those motivations are gone now for me. I think it's still a very viable candidate, and it's definitely worth exploring for sure. And we are doing that. But yeah, my view is that it's a better strategy now to just look everywhere, cast a wide net and try to look for other things. And that's what the community has been moving towards in the last few years. So in 10 years ago, it was all WIMPs, essentially. Since then to now, the light dark matter candidates have exploded, but also other options. So people are more open-minded about what it's meaningful to look for.
For Luca, you were mentioning in the first lectures that you were searching for displaced vertices. I don't know if you were searching for the same type of signal in this fixed experiment happening in CERN. That was just like a question because I was wondering, you're going to involve in your research maybe long-lived particles. So what's the lifetime you're expecting for them to have in this experiment?
Oh, well, it's really depending on the region of parameter space. So unfortunately, the lifetime of the particle, especially in the visible decay scenario, so where if you talk of a dark photon model, obviously, if you consider the visible scenario and you think how is the dependence of the lifetime on the parameters, it goes as a epsilon squared, and epsilon goes from 10 to the minus 2, and it's still reasonable to search up to 10 to the minus 9. So there are really many possibilities. There are regions that are accessible for search of displaced vertices on a fixed target, for example, like HPS does. And HPS has a sensitivity in terms of displaced vertex, which is of order of tens of millimeters. So we are expecting a particle produced with a GeV, order of magnitude of energy, to travel of order of millimeters. But also you can have a very long-lived particle. For example, today when I talk about E137, they were searching essentially Alps actually, but they were reanalyzed in the context of dark photon, which travels for hundreds of meters. So very, very differently. And again, you arrive to the level that if you go down and down the parameter space, you have particles that travels for kilometers, so you probably will never be able to unless thinking of something very specific, to address the displaced vertex with a particle physics search.
So maybe for this concrete experiment regarding fixed targets happening in the CERN that you mentioned, would be like a few millimeters, maybe for it to not decay right after the detectors.
Well, basically you have to decide when you I don't know if I got correctly the question, but if you decide, when you think of an experiment, you decide which part of a parameter space you want to target, and when you build it by consequence of the properties of the particles, which are consistent with the parameter space. So, for example, HPS wanted to search in the thermal target, which was a JLab actually, and they thought of an experiment capable of detecting displaced vertex up to a few millimeters. So, if you want to explore or think it's reasonable to search for something else, you maybe will try something different. So, for example, beam dumps with a large decay volume, or for example, like SHIP will be doing with this large decay tube to allow particles which are more long-lived than a few millimeters to decay. Also, you have to take into account the energy at which you are producing this particle, because the more energetic they are, the more they can travel. So there are many variables, and really depends on. You have first of all you have to choose what kind of particles and what part of the parameter space you want to search for, and then you build your experiment. There are some regions that you cannot explore with a displaced vertex search because they decay promptly, and you have to be simply aware of that.
Okay, thank you.
Thanks. So I can take one more question if you want. No? Okay, so if not, we thanks again the three speakers. And now it's time for lunch. People that have to go to the USP, we meet outside. I see you tomorrow 5 minutes before 9, right?